Geology of National Parks class, let's talk about our very own national park, the Florida Everglades. 1.5 million acres, or 2,354 square miles. It's huge. It was established in 1947, and it's the largest remaining subtropical wilderness area in the United States. Florida is quite unique in that it kind of dips down into subtropical latitudes, goes pretty far south, and the fact that its bedrock is limestone and there isn't much gradient, very flat, makes this a very unique and one-of-a-kind ecosystem and landscape in the United States. If you consider the greater Everglades area before Florida was heavily developed, it essentially would start at 25 degrees north, 82 degrees west, and on average only about 7 feet above sea level. Those coordinates essentially span from northern Florida near Lake Okeechobee down to Florida Bay, and that total area is about 19,000 square kilometers. Here's a park map. Okay, you can see the boundaries of Everglades National Park in green here, and above it is a big cypress, and then there are water management areas that surround some of the areas to the northeast. And it's a very unique wetland because the way water flows in this area. It's a river. Geologists consider this sheet flow. So it's a sheet flow in ecosystem. That's water that kind of moves really slowly on a very low gradient, meaning that it's not steep, very flat-lying area, but the water moves very slowly, and it actually moves. And it might not seem that way to an untrained eye, but the direction of the overall water flow in the Everglades is towards the southwest. It receives much of its nutrients from rainfall, not from the erosion of existing outcropping rocks. Right? We don't see too many of those here in Florida. And so it makes it independent of rivers and streams. There are two main major wetland types there. There are swamps and marshes. And Everglade swamps are mangroves and cypress swamps. Non-woody marshes make up the Everglades. And the typical environments we run into are freshwater marshes, wetland tree islands, and you can see that in satellite images of Everglades National Park. You can actually see the kind of teardrop shape of those tree islands. Cypress heads and tidal creeks as soon as you get a little closer to the ocean. So here's the historic Everglades, and that includes the Kissimmee River, so just south of us. This would be considered the entire kind of drainage basin of the Everglades before heavy development. Okay, this is the historic flow. Okay, so the Kissimmee River just south of us, Lake Toho connected to a bunch of the lakes to the south, and then that river kind of winds down into Lake Okeechobee, and then Okeechobee just used to freely flow down into the Everglades. Okay, and so most of the year during the rainy season, this was completely inundated in water. Plus or minus these areas on the side, these could be drier. In the dry season, a lot of times these areas were completely dry, and then the river kind of gets a little narrower during dry seasons. So if you're right smack into the Everglades, this is what you see. It's a river of grass. It's this sawgrass. A lot of people kind of dislike them if you're kind of walking through it. Most people would just go visit during dry season so that they're not actually wading through the water itself. But the sawgrass itself can be kind of sharp and can cut you, so you got to wear long sleeves. Most people explore this area using airboats, right? Because you can just go right over the sawgrass itself. But there are areas that are specifically kind of navigable areas where you're allowed to kind of move in and out so that you don't damage all the sawgrass in those areas. And then just outside the kind of central part of the river of grass, what you'll see are these ridge and sloughs. Okay, sloughs are kind of low-lying areas where you get faster water flow. The elevation difference between a slough and a tree island could be a couple inches to maybe half a foot or a foot. And then here are those teardrop-shaped tree islands that we talked about. A lot of these places are very isolated, not visited, because we can call it a tree island, but when you step into it, it's surrounded by water, and as you go in, it's only a few inches higher than the surrounding slough. Some people like to go orchid hunting into these areas, but they're very beautiful. But the teardrop shape kind of indicates the direction of water flow. Okay, and so you can kind of tell if you look at a satellite image of the Everglades, you'll notice that a lot of the tree islands are shaped in this direction because of the southwestern sheet flow of the Everglades water. The term river of grass was kind of coined together in 1947 by Marjorie Stoneman Douglas. And she published a book on the Everglades called The River of Grass. And it was really like a call to action for people in South Florida and Central Florida about how beautiful the Everglades were and its suffering and its deterioration through the development movement, really, in agriculture. Most people at the time, and those ideas kind of continue to persist today, but people consider the Everglades kind of like a useless land that you can't build a huge strip mall on, or a residential area, with cookie cutter houses and all that. It's just you can't farm on it or anything. But in reality, what Marjorie really pointed out to was the beauty in this unique wetland area. That there are hundreds of birds that call it home. A lot of migratory birds use it as a stopping area to rest before they continue on in their journey. Immense number of different types of species, from reptiles, alligators, snakes, turtles, other lizards, and they all exist within this wetland, and it's can be very beautiful. And so in the summer wet season, you guys are all familiar with that, the afternoon thunderstorms and rain showers. That's when the grassy river becomes really wide because it's swelling with a lot of water. And in the wintertime, typically mid to late November up until March or April, that's when it can kind of narrow down and some of the areas completely dry out. Okay. And sloughs are kind of like deeper portions of the river, and they deliver a lot of fresh water to these different areas of the swamp. So here's that historic flow that I've showed you before. Let's look at some different environments. Hardwood hammocks are areas that are really close to the edge of sawgrass plains, and here you see hardwood trees, oak trees, cypress trees, and there are areas that are rarely inundated with water, but they can be. And so you see a lot of the hardwood trees. And then when you go to higher areas, and this is, you'll find a lot of this in Central Florida, but there are these pine forests. Okay, these are slash pine that grow kind of symbiotically with these sawgrass over here. And they grow in kind of sandy soils. These are really kind of skinny trees that grow up really high. You'll find this environment a little further away from the River of Grass, or the Everglades National Park. And then there's the Marl Prairie. You find this further south. I don't know if you guys have ever driven on US 1 just south of Miami. if you're like heading to the Keys, there's an incredibly flat area that almost seems endless, and there's nothing out there. That's the marl prairie. Marl is just a type of soil that contains a mix of different materials, sand. But what makes the marl prairie unique here is that it has broken down limestone, essentially, like limestone mud in it. All right, hammocks. These are areas where you have hardwood trees that grow just a few inches above the low-lying areas. They're protected from fires during the dry season. Ferns and air plants thrive in these kind of moisture-rich hammocks within that area. And what you find are oak trees, red maple, hackleberry, gumbo limbo, and mahogany are typical species of trees you find here. Now, when you get closer to the coastlines, what you'll see are a lot of these mangroves. Okay, they almost look like these tripod trees that kind of grow right into the water. They're covered in water most of the time, right? The tide rises up and falls, and these guys kind of remain in place. They grow in brackish waters, meaning water that is salty from the ocean, but there's an influx of fresh river water, and that river water is the Everglades water that's kind of coming down south to the southwest. And so that helps here. This helps stabilize the kind of coastline in this southwestern portion of Florida. There's a lot of these mangrove areas, and they're very important. A lot of them are kind of, it's a unique environment. They're kind of breeding grounds for a lot of ocean organisms. And then there's Florida Bay. Florida Bay is out here amongst all these kind of little dotted islands. It's almost like the area behind a lot of the, like Key Largo, Isla Morada. These areas are kind of shallow areas made up of brackish water, a little saltier, just a little mix of fresh water coming from the Everglades. You'll find a lot of carbonate muds in this area, and again, it's a nice area of shallow water and breeding ground, and nursery for a lot of ocean organisms here. The mangrove forests in the coastal areas surrounding the Everglades, they kind of are on the fringes of the winding rivers in the southern tip of Florida. And there's 3 species of mangroves found here: red mangroves, black mangroves, and white mangroves. I find it difficult to tell them apart, but white mangroves have rounded leaves. Red mangroves have this prop roots. Okay, in the Florida Bay Area, that's the largest body of water in the Everglades. That coastal system is unique because of that type of, in that latitude, the climate and the warm ocean water and the influx of fresh water coming from land. You can't really find that in many other places. The sea bottom there is covered by seagrass beds, and it's a feeding grounds for a lot of organisms, nurseries, and a refuge for wading birds. And I've kind of kayaked in some of the areas behind Isla Morada, and you see a lot of different organisms, mangrove tree islands, nurse sharks, jellyfish, all kinds of different fish there. Oysters, sponges, shrimp. Great seafood, by the way. So here's some other images of what the Florida Everglades is like. Look at this nice relationship amongst alligators and wading birds. There's a great blue heron right next to an alligator. No big deal, right? And so here are some of those. You can see some of these elongated tree island areas or hammocks. So the history of the Everglades hydrology kind of begins about 5,000 years ago. I mean, the Everglades really is at the mercy of rising and lowering of sea level. So over the past 5,000 years, sea levels kind of been rising but not too quickly. And so Florida has been accumulating peat soil. Peat soil is a very organic, rich soil that will form in bogs or swamps where there's um, uh, water with lower oxygen levels. So carbon-rich material will accumulate. That's what makes those soils organic rich. So the presence of surface water on Florida really changed the vegetation to marsh, which marsh plants, which are more tolerant to salt water. And the Everglades vegetation, as sea level is rising and continues to rise, is starting to advance into higher and higher grounds. Okay. And over the course of 5,000 years, this created the kind of Kissimmee Lake and Okeechobee Everglades watershed or drainage basin. Now, Florida, in the early years, most people lived on like the Atlantic coastal ridge of Florida because really the Everglades were just unlivable. Imagine living in Florida without air conditioning or screens. There are stories of just crazy mosquito clouds that would just move in and just eat people alive while they were there. And so not many people ventured out into the Everglades and the river of grass. They kind of stuck to close to the coastline. That gave kind of a consistent ocean breeze, and it's higher ground, so it wouldn't be continuously inundated like many of the areas on the interior of Florida. So what a lot of industrialists and developers wanted to do was drain the land area in Florida, drain those swamps, dredge canals, and get that fresh water out into the ocean and dry up the land so that they could build cities. See, a lot of people at that time were living in the Northeast, Philadelphia, New York, Boston, DC, and a lot of people wanted to live in places that have much better weather, which Florida does. And so many people tried and failed to start up new towns and cities and start real estate companies. One of the most notable ones was Hamilton Diston. He was a rich industrialist from Philadelphia, a really smart guy, and he decided that he wanted to take on the Everglades and drain it, which up until that point many people had tried before and failed. And so he wanted to reclaim about 12 million acres of land, or 1/3 of the state of the Union at that time. He was from Philadelphia. He owned the Diston and Sons saw manufacturing company, and so he was really rich and motivated. He got a lot of engineers to go down and start creating canals to drain the swamp, to just go out east or west into the ocean, and also channelize the existing rivers and straighten them, narrow them, dig them deeper so that more water would efficiently drain and go out. And so here's an example of the Diston, 4 million acres, the Kissimmee Land Company, and their goal was to drain a bunch of land in the Kissimmee area and then sell it and start kind of creating development in Central Florida. This was in the late 1880s. And so what they did was here's some new channel construction in the Kissimmee area, and then they dredged the Kissimmee River so that it would be deeper, and then water would flow faster into Lake Okeechobee. And then the idea was to also dredge the Caloosahatchee River so that more water would drain out into the ocean. So this was the first large-scale drainage effort in Florida. And there was some initial success. There was a lot of initial failure as well. A lot of the workers died because of the poor working conditions. Malaria is a problem, and event, ultimately they drained a lot of the areas and started selling real estate, and there was some new construction, but ultimately, one rainy season, after most of the work was done, all the areas they had cleared and dried out flooded again, and yeah, and Diston's company went belly up. He kind of lost his fortune, drained all his money on this project, and he ended up killing himself in his bathtub in Philadelphia. Kind of sad. But then the effort was then taken on by other entities, federal government, and they began to build canals to help drain this area. And again, this is much later, almost 30 years later, or I'm sorry, 50 years later. And technology improved, the dredging technology improved as well, so that this could be undertaken. But a lot of these canals were agricultural related canals, and the purpose was essentially to get as much water from inland Florida out into the ocean. So they went through the port, essentially Port St. Lucie out to the ocean, and then the Caloosahatchee River through Fort Myers out this way. And then these are those kind of additional canals that were dredged right through and go through various portions of South Florida. This one going right through Miami. So that was the next major Everglades drainage project. So now that giant ecosystem, the river of grass, that kind of very unique area, was now replaced by sugarcane fields. In fact, just south of Lake Okeechobee are the largest sugarcane fields in the United States. And other than sugarcane fields, there are just huge areas called water conservation areas. Just areas where they don't do anything really. They just let water accumulate there. It's like a reservoir kind of. But the only reason those agricultural fields are in use today, and the only reason it's profitable, is because of the U.S. trade embargo on Cuba. So as soon as that was ramped up, then that made growing sugar in Florida profitable, and that's the only reason why really they're there. Otherwise, I mean, if it was up to free markets, they'd be belly up pretty quick. But disaster awaited. Hurricanes, as every season kind of comes along, they hit back then too in 1926 and 1928. Some hurricanes that kind of went through the center of the state dumped a lot of rain, and that flooded a lot of the surrounding areas. So they realized that the canal dredging projects and narrowing and channelizing wasn't sufficient enough. Here are some images. This is Belglade in 1928. This is downtown Fort Lauderdale in 1926. Fort Lauderdale was the kind of spring break spot for a lot of people on the East Coast. I guess it still kind of is, but it's an older crowd now. So here it is. So the next big project was the Herbert Hoover Dike, south side of Lake Okeechobee, just to kind of prevent the flooding that had occurred in the kind of 5 years before that. And that's still operational today. It's still it's not in great shape. You can visit it, but it's in need of major upgrades, and that dam could fail. Right, and here are those canals. That one goes right through Palm Beach, some through West Palm Beach, and this one right through Miami. Okay, so here is the areas that flooded later on in 1947. So major areas. This went all the way to the coastline. Some of the Atlantic coastal ridge areas here couldn't have flooded. They're pretty high, but still, this is huge areas that were flooded because of years of heavy rain and perhaps even hurricanes. So in the 50s through the 80s, there was a Central and Southern Florida project where 1 million miles of canals, 720 miles of levees, and over 200 water control structures. Like, see, I don't know if you can see this here, but there's a water control. They're kind of like those artificial floodgates that you can lift and close and manage the water movement from canal to canal. Those were built during this time. Army Corps of Engineers was involved with that. Okay. And what we see here's south of Lake Okeechobee. Here are where a lot of those agricultural farms are. And the reason why they're kind of good places to farm is because of that peat soil that we talked about. The peat soil is very organic rich, so you can kind of grow your sugarcane. In fact, you can see some here. It's kind of, I don't know if you've ever seen sugarcane before, but you can just cut a stalk off, rip and machete off kind of like the outside areas and just chew on the sugarcane. It's really sweet. Nice. Anyways, but what's happening here is that because they've been farming on this for so long, there's a lot of soil erosion, and the land surface has sunk as a result of it. Here in Florida, our bedrock is limestone, okay? And what we've noticed is that there was over kind of 20 feet of peat soil deposited in these kind of central areas just south of Lake Okeechobee. But since agriculture kind of began, a lot of this is eroded away, and this is kind of like what's left over, essentially. It's just a thin veil of what it used to be. And that's a lot of the agricultural areas here. You can see how dark that soil is just by looking at this picture here. Other problems that affect the ecosystem here are invasive species. There are over 68 plant and animal species that are threatened or endangered. Now, these are local species. 1.5 million acres are infested with exotic plants, and that's people from other countries, other states kind of coming in and bringing these things by accident or sometimes on purpose. In the case of, I guess the well-known case is the Burmese python. That was brought on purpose. People brought those as pets. And what happens is those things grow pretty big, and after they kind of exceed your height, when they grow 6 feet or larger, yeah, they're tough to maintain, keep feeding. And you know, I don't think snakes are loyal. I think if that thing ever got out in the middle of the night, I think it wouldn't think twice about eating you. So I think a lot of these people who own snakes eventually, or Burmese pythons, eventually just let them go in the Everglades. Now it's a really big problem. The Florida Wildlife and Gaming Commission, they actually pay people to go out snake hunting and kill as many of these invasive Burmese pythons as possible. But it's really an uphill battle. They can hide in the smallest crevices, areas, and underwater. So I doubt they can get. They're not going to get them all, but I guess controlling the population can help a lot of the local endangered or threatened organisms. But plants are just as bad too. I've seen this in Orlando. This is the Brazilian pepper. It's non-native plant that's everywhere. It has these like distinctively red berries, and it grows really dense and prevents the growth of other vegetation. So it's really kind of dominating the landscape in some areas. Okay, so then in the 90s, that decade they planned for the comprehensive Everglades restoration plan, and this was really a fantastic work. Hydrologists, environmentalists, geologists all got together and kind of built this plan to kind of restore the Everglades to what it used to be. Okay, here's the it was approved in 2000. Okay, it includes 60 or more elements, and it'll take over 30 years to construct. So that goes well into 2020. Okay, the estimated cost is $7.8 billion. So it's a plan that includes all kinds of stuff. The building of more water storage areas, the purchasing of agricultural lands, and water conservation areas, like kind of combining those areas, and then restoring the original environment. But here, let me just show you this image here. This is the current flow or water flow in the Everglades, right? We built all those canals, and that heavily diverts water right into the ocean. And what that does is that starves the lower part of the Everglades, right? It doesn't receive as much water as it should. And these areas can be dry for the majority of the year when they used to be completely inundated in their historic flow. So that's heavily altered the ecosystem in South Florida. And so what the plan is to kind of restore a portion of that flow. So that is to divert a lot of water instead of out into the ocean into these water conservation areas, and then allowing that water to kind of run its historic path to the southwest. And that'll kind of bring a lot of fresh water into these areas, and hopefully a lot of the Everglades vegetation can kind of make a comeback as it grows back towards the ocean. Remember, if you kind of cut off the fresh water and divert it into the ocean, kind of salty, brackish water will move inward, and that's what's been happening in southwest Florida over here in the border of the Everglades. Okay, but there are a lot of constraints. We have a lot of urban water supply and flood control needs, right? We want to prevent floods from occurring, and if we allow a lot of water to go into the Everglades, that could increase odds, but part of the plan was to build a lot of water management structures. Also, the agricultural business, they're very powerful, have a lot of money, lobbyists and stuff like that, so there's a lot of agricultural land standing in the way of connecting the Everglades to Lake Okeechobee. Lake Okeechobee itself, because it's dammed, and they have their own issues with blue-green algae and a lot of the fertilizers that run off into the lake and cause those algal blooms. Also the invasive species, that's a problem we've talked about. And also water quality, because a lot of the water conservation areas are right south of these agricultural areas where they kind of use a lot of chemical fertilizers to increase crop yields, and that runs off into some of the canals that they dredge, and then that goes right into the water conservation areas, which goes into the Everglades, and that causes certain local species to be outcompeted by invasive species because of the changing in nutrients. So those are some of the issues. So here's a GIF showing you the pre-drained system throughout an entire year. Here are the months going back and forth. And then this is the, hopefully after the comprehensive Everglades restoration plan is put into place, what the water flow will look like. So fingers crossed. All right, so now let's get into the geology or the book concepts and slides. Since we're talking about the Everglades, we're talking about water on the Earth's surface. And water on the Earth's surface is mostly ocean water, 96.5%. Okay, all the fresh water, meaning the water doesn't taste absolutely nasty, filled with dissolved solids, that's fresh water. That only makes up 2.5% of total Earth water. And if we break that 2.5 down into, so like what is that 2.5%? The majority of it are locked up in glaciers and ice sheets, very far away from where we are. Groundwater is the kind of the most usable, ready freshwater source for us to use. All the lakes, all the rivers, all the water in the Everglades, Lake Okeechobee, Lake Toho, Lake Titicaca, Lake Ontario, right? All those lakes only make up about 1.3% of the 2.5%. So that includes major rivers, Ganges, Amazon. So if you break down that superficial water, 1.3%, most of it is actually snow and ice. So lakes, like we've talked about, only make up 20% of that, and swamps, I guess Everglades would fall under that, or swamps or rivers. I'm not sure how they classified that. But that in total would be only about 3% of this 1.3%, which is only, of that 2.5 total water percent. I've confused you completely. Let's move on. So the hydrological cycle is just understanding how water moves through all the different reservoirs. How it moves from the oceans to land to rivers to lakes to groundwater through plants. Okay, and essentially, like water can move through all of these reservoirs through a number of processes. Okay, water leaves the atmosphere via precipitation, so snow or rain. Okay, and then that raining water can either soak into the ground, we call that infiltration. It can run off the surface of the earth and into rivers, or it can evaporate, or it can be stored at high elevations in a snowfield or a glacier. So this cycle is balanced. We're not losing any water anywhere. They're just moving from one reservoir to another. Right? The only addition, so to speak, would be outgassing from volcanoes. So essentially, here's the cycle. 320,000 kilometers of ocean water is evaporated into the atmosphere. About 70% of that just rains back down onto the ocean. All right, these are cubic kilometers, so kilometer by kilometer by kilometer. Okay, 96,000 cubic kilometers rain on land or snow. All right, some of that is stored in the mountains, glaciers, and snowpack. Other amounts of that water infiltrates the ground, becomes part of the groundwater reservoir, and the rest runs off. And that runoff can lead directly into the ocean, 36,000 kilometers approximately every year. And then about 60,000 cubic kilometers either evaporates or transpirates. And transpiration is when plants use up that water and they convert that liquid water into water vapor, and it moves through their leaves. It's essentially the same process as evaporation. So geologists, earth scientists just kind of use like a word smash and put those two things together and call it evapotranspiration. So the differences between whether water will run off on the surface of the earth or infiltrate into the ground really depends on the conditions of the landscape and the conditions of the rainfall. If it's very intense rain and long lasting, then that means a lot of that water will run off. So just imagine like an afternoon thunderstorm and we get heavy rainfall. The water will start to pool on the surface of the earth pretty quickly. But if you get a light drizzle, that'll just kind of coat the ground and slowly percolate downwards, and more of that will actually infiltrate rather than run off. So if you have heavy rainfall, then the surface will get saturated really quickly, and then most of that water will run off. Okay. If the soil's already saturated, then that means if it rains on that soil, most of that water will run off. If you have soil that has a lot of clay in it, clay is impermeable, so when it rains on clay, that'll make the water run off instead of infiltrate. If you have soil that has a lot of sand in it, that will allow sand to kind of percolate through the ground and infiltrate rather than run off. Also, the slope of land is important, because if you've got kind of heavily sloped land or steep land, you'll have more runoff than infiltration. If you have flat-lying areas, then you'll have more infiltration. And then the nature of vegetation cover. If you actually have a lot of plants, trees, and brush and stuff like that, the roots will help water infiltrate into the ground, and it'll help hold a lot of water. Really dry areas that have very little vegetation cover, surprisingly, a lot of the water will run off because the areas are so dry. It'll hit the land surface and then run off real quickly instead of like following the plant's roots deeper into the ground. And so when the surface is impermeable or saturated, runoff is dominant. And so in urban areas, like where we have cities, we put down a lot of impermeable pavement. And so what that does is that diverts a lot of water. It channelizes it into specific areas. So buildings, roads, and parking lots create a lot of runoff. So once running water begins to run off the surface of land, it starts off as sheet flow, like you would see in the Everglades. And then sheet flow will develop into tiny channels called rills. Rills meet to form gullies. Gullies form brooks, then creeks and streams. And streams are just any water flow in a channel, regardless of the size. And so rivers can carry a substantial amount of water and have a lot of different tributaries. Here's an example of a river that is a meandering river, kind of flowing back and forth in these huge winding bends. So a drainage basin is an area of land that contributes water into a channel. You can think of, if you look at the image here, this entire area that's highlighted in kind of green or light green is a drainage basin for this channel right here. And the drainage basins are divided by high lying areas or high elevation areas. We call those divides. And sometimes it's hard to tell in flat lying areas like in Florida, but typically they follow the ridges of mountains and hills. And when you have very large drainage basins, they can be divided up by larger divides called continental divides. So the best example of this is at Yellowstone National Park. The continental divide of the Mississippi River drainage basin goes through that national park right here. Okay, there's a big sign that lets you know that too if you ever go to Yellowstone National Park. But here's the largest drainage basin in the United States, the Mississippi River drainage basin. If it rains anywhere in these kind of drainage basins, that water will run off and flow through the Mississippi and out to the Gulf. Okay, and then here on the east side is the Appalachian Continental Divide. So river systems drain the land area. There are very few exceptions in polar areas and in deserts where there's very little precipitation. You might not see any rivers. The variety of the different types of rivers really reflect the variety of environments that they're found in. Climate, plate tectonics, and human intervention can influence or change the character of a river. River systems can be divided up into three areas. One is the area of sediment production, another is the area of transportation, and the other is the area of deposition. So the headwaters of the river are typically at higher elevations. This is where rivers begin. And there are a lot of little contributing tributaries into kind of the main artery of the flow here. This is the zone of sediment production. And it's a zone of sediment production because a lot of erosion and mass wasting occur here. The bedrock's exposed at the surface, higher elevations, and sediment is produced here. So there's more erosion than deposition. Then as the river approaches lower lying areas, like the middle portions of a river, where the river kind of gets a little wider and starts kind of winding back and forth and meandering, that's the zone of transportation. Here in the zone of transportation, erosion and deposition occur at somewhat equal rates. And then the end of a river, or the mouth of the river, is where the zone of deposition is. And this is where the vast majority of sediment being carried by the river is deposited in deltas, where rivers meet another body of water, a reservoir, or the ocean. So this is a nice picture of headwaters to a river. Bedrock's exposed, water's doing its work of physically and chemically weathering the exposed bedrock and generating sediment, essentially. Sediment's generated by breaking the bedrock into smaller pieces, bank erosion, and also scouring downwards. Its erosive power is focused on cutting downwards through the bedrock. The sediment transport area, it's in balance. There's a lot of erosion and deposition. You can think of that as this over here. And this would be like a river delta, okay? This is the area of sediment deposition. This is just sediment that's been eroding from higher areas, and all that sediment depositing as soon as the water velocity slows down and hits a bigger body of water, and then you get deposition like that. There are many different types of drainage patterns. Okay, we'll talk about these four. Let me just go straight to the pictures. The most common drainage pattern is dendritic, which is this here. This forms when you have uniform surface materials. And what it looks like is a tree without any of its leaves. Okay, so here you have smaller orders of the river kind of contributing to the main artery. The flow is in this direction. And all the water kind of contribute into a larger stream, then contributes to the main portion of the first order area of the stream. All right, and so this is just kind of a pattern that develops. It's very common. The radial pattern is if you have any major landscape feature like a volcano, you'll have channels that just radiate away from that main structure. So the flow is in this direction, that direction. They're just radiating away. Okay. This is the Minecraft type drainage pattern where it looks like it just follows these straight paths. Okay, and that's because it's moving through bedrock that's heavily jointed or highly jointed on these like parallel cracks. So the river looks like it's following these straight paths and then sudden changes. And then finally, there's the trellis pattern. The trellis pattern is interesting because it's bedrock that's exposed that has different rates of weathering. So you have a very resistant layer, which would be right here. And then here in the valleys, you have a weaker rock, less resistant. So what will happen is the water will flow along the less resistant rock here, has eroded away, so it's a lower lying area. And then as it kind of moves in this direction, it jumps a gap over the more resistant rock in one place. We call those water gaps. Okay, they're often places where you'll find kind of rapids or waterfalls or something like that. And then the water will resume, this water will kind of flow along the less resistant bed and then jump over the more resistant bed just in one spot. That's the trellis pattern. Streamflow is kind of like how water moves through a river system. You can have two. One is laminar flow. That's where you have nearly water flowing in a nearly straight path. That's the Everglades. That's the sheet flow, non-turbulent water. You can see an image kind of representing that over here. Then you can have turbulent flow, which is this. It's extreme whitewater rafting, and that's where water moves in an erratic fashion, both horizontal, vertical, moving upwards, being kind of diverted by rocks that are in the channel. Okay, so streams typically exhibit turbulent flow, and that's why the Everglades is such a unique environment, because it's a river, but it doesn't have that turbulent flow. Now, there are many factors that affect the flow velocity of water in a river. The most obvious is the slope. If you have steep slopes in a landscape, that'll create, that'll allow for more gravitational energy, and water will flow faster because of a steep slope. Obviously, if you have a lower gradient like you do in the Everglades, water flow is much slower. Also, the channel shape affects the velocity of the water. The channel itself, like the channel bottom, has this area called the wetted perimeter. And that's the area that comes into contact with the water. So if you have a very wide channel and shallow channel, more of the water is going to come into frictional resistance against the floor of the channel bed. Okay, and that slows down the water. If you have a narrow channel and very deep, that limits the surface area that comes into contact with the channel bottom, and then offers less resistance, so you'll have faster flowing water in a narrow channel. Okay. Also, the roughness is important, the channel roughness. If you have rocky channels like boulders, that creates a lot of turbulence and decreases the velocity. If you have channel bottoms that are very silty and smooth, that will allow for easier flow, faster velocity. And stream flow is important. The amount of water, its velocity, or the amount of water, the discharge, that's the volume of water flowing past a given unit of time along a river. So what happens is if you have discharge increases, so an increased volume of water moving through the river, the width, the depth, and the flow velocity all increase at the same time. And we have an entire government agency that monitors this. And the USGS has over 7,500 stream gauging stations where they take a look at flowing water in different river systems. And that's important because of resource management, especially out west. They want to be able to store water or get rid of it if some of the reservoirs are getting too big. And also protect low-lying areas and communities. If they know there's a major storm or low-pressure system coming in, dumping in a lot of rain, some of these low-lying areas close to the ocean might be vulnerable to flood. And so if you can measure the amount of discharge in some of the areas in the mountains, then we can warn coastal communities of incoming cresting river as that water makes it down towards the ocean. Running water does a lot of work. It moves a lot of sediment and does it in 3 different ways. One is the dissolved load. That's invisible in the water, okay? Water carries a lot of dissolved solids in them, okay? Calcium, sodium as examples. The next is the suspended load. And so the water itself will carry material in suspension. And these can be little pieces of fine sand, clay, or silt, and they just float around in the water. And then ultimately, the bed load, this is just kind of boulders and pebbles just skipping along the bottom of a channel, and the water just kind of pushes it down the channel. That's how it kind of moves sediment around. The dissolved load is delivered to the river via groundwater. So groundwater contributes a lot of water to rivers, and it contributes a lot of dissolved substances into it. And so the dissolved load, or the amount of dissolved solids in the water, is not affected by stream velocity. You can have the fastest flowing streams or the slowest flowing streams. The dissolved load is unaffected. What does change the composition or the amount of dissolved load in the water is if you have organisms creating hard parts. Okay, they'll remove calcium from the water to create their shells. So sometimes you'll see like little clam shells or something forming, or snails. They got that calcium from the water, and that would lower the dissolved load of the water. If the river enters a really dry area where the evaporation rate is high, that means the dissolved load concentration would increase just because you're removing pure water from the river, and the concentration would increase as a result. The suspended load is typically just sand, silt, and clay. The amount of material carried in suspension is completely controlled by the stream velocity. You have faster moving water in a river, it's going to carry larger pieces of sediment. If you have more discharge or more water, it can carry more sediment in suspension, but faster moving water will carry larger sediment in suspension. And that's because particles of different size have different settling velocities. If you have a larger particle, it's heavier, you need faster moving water to keep that in suspension. So if water velocity slows down, sediment in suspension will deposit. Okay, look at this river. This is completely light brown. It's carrying a lot of sediment within it. Silt and clay most likely, that's what's giving it that muddy color. And over here we have on the y-axis stream flow velocity in centimeters per second. And here we have particle grain size. So the smallest stuff, clay, and the largest material, pebbles, anything that has a diameter greater than like 10 millimeters. Okay, and then this line here is the settling velocity. So if any size particle is above this red line, it remains in transportation mode. That means it's floating around in the water. If any size particle is below the settling velocity, that means deposition will occur. So let's take an example. Say we have water moving at 100 centimeters per second. That's 1 meter per second. That means you can draw a line straight out here and then straight down. And that means all of this material that's smaller than, what is that, 12 millimeters in diameter, will be in transportation mode. Okay, that means it'll be floating in the water because that water is moving pretty quickly. Anything larger than that, so if we draw a straight line here, anything over here would deposit out because it's too large, its settling velocity is too high. Okay. If we look at, say the water velocity slows down from 100 centimeters to 1 centimeter per second, so we can draw a straight line out here. And so what this means is that most of the sand will deposit out, okay, because it's in this area underneath the curve, right? If you keep drawing this out. So all this material will deposit out. And the only things that will remain in suspension are the smallest of sands, silt, and clay. So that's what happens when you drop in velocity or go down in velocity. What will happen is that you get deposition. All right, deposition of sediment. And then finally, you have the bed load. And this is just coarse sands, gravel, boulder, kind of moving down along the river. These larger particles can be moved down during the flood stage, which typically occurs in spring, and that helps push material down the river channel. Okay. There are two terms here that you need to know. One is capacity, the other is competence, and these describe a stream's ability to carry solid particles. Capacity is the maximum load of solid particles in a stream per unit time. So that's affected by the discharge. Okay, the more discharge, the more water flowing through a river, the greater the capacity. Think of like a river as like a conveyor belt carrying sediment to a new depositional environment. If you've ever been to the Mississippi, which is pictured there, it's huge. It's really wide. Not the fastest moving water. In some areas, yeah, sure, it's fast moving, but it's not the fastest moving water, but it's really wide. It's got amazing discharge. There's a lot of water moving through the lower areas of the Mississippi River. And so its capacity is unparalleled. Well, you could compare it to the Amazon or the Ganges River, but its capacity is very large. Its competence, however, isn't very great because of its slow moving water, or slower moving water. If you have rapids or fast moving water, that's high competence, meaning it can hold maximum particle sizes that are much larger. Okay, so streams with faster velocity have higher competence. All right, let's talk about some of the features that rivers can deposit out into the landscape and into the ocean. Anytime you have deposition, here's a dried out river or an ephemeral river that only flows during certain times of year. It's depositing out a lot of sediment. Okay, this is all alluvium. Sediment that's deposited by a stream we refer to as alluvium. Okay, and in some cases, we'll find deposits of particles of the same size, and we'll refer to that as well-sorted alluvium. And that means that whatever mechanism deposited had a very constant velocity because it carried particles of the same size. There are also different types of stream channels. Bedrock channels are river channels that cut directly into the bedrock, and you can see one pictured here. This are typically at the headwaters of rivers or the beginnings of rivers because you're at a higher elevation, bedrock's closer to the surface, the rivers cut down into the bedrock and expose that rock. And so here you'll see energetic water flow, typically because there's a higher gradient, steps, pools, potholes, rapids. Those are all typical of headwaters and also bedrock channels. And the pattern is controlled by whatever the rock that's exposed. Alluvial channels are a little different. Typically you find these in the kind of sediment transportation zone of a river or at the mouth of a river. Alluvial channels are typically associated with floodplains, flat-lying areas that are prone to flooding. The channel shape is affected by the size of sediment, the gradient, and how much water is flowing through it, and the patterns reflect the stream's ability to transport the sediment at a uniform rate while expending the least amount of energy. And one type of alluvial channel is called a meandering channel. And a meandering channel kind of keeps suspended sediment and moves in these broad sweeping bends that we call meanders. They're kind of like airport security lines. You know how you kind of start here, you go over here, you go back and forth and 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 back and forth until you get to the security guy. Makes it really awkward when there's nobody in line and you're pretty close to them, but you have to just run through that maze. Yeah, those are meanders. Okay. And so meanders evolve over time. They change. So they start off, and they. So let's say we have a river kind of meandering slightly through time. Over time, the meanders will get larger, and the loops get crazier and larger. But then they straighten out, and evolve because what happens is you have two areas called cut banks and point bars. Cut banks are areas of erosion. Point bars are areas of deposition. Okay, let's take a look at this. Here's a meandering river, and this area here is a cut bank, and this is where erosion occurs. And erosion occurs here because the water moving along the river meets its maximum velocity really close to the channel wall. Okay, so you have high velocity water moving here, and that erodes and scours this area away. So it's kind of making the loop larger, and over time it's going to make that loop larger and larger. It's going to be pushing in this direction. And it's a shame. If you built your house right on a cut bank, that means your house is going right in the water. On the other side of a cut bank, what you'll find are point bars, and that's an area here. This is an area of deposition. Here you can, a lot of times you see sandbanks, because here is where the velocity of water is the lowest, and when you have low velocity water, that means it's going to dump its sediment load and deposit, and so we call those point bars. So if you have a point bar here, then you have a cut bank here. Here we have a point bar at the next bend. Here's another cut bank, and so this is going to evolve and continue to move in that direction. This is going to evolve and move in that direction. Here's an aerial footage. You can see here point bar, cut bank, point bar, cut bank, and so forth. Point bar, cut bank. All right, so that's how meanders kind of slowly evolve as they erode and deposit in different areas. So what happens is, please watch this video. It helps show you the evolution of meandering rivers. But what happens is that here's a meandering river, right? It's going back and forth, and then right here, this is a cut bank, okay? And then it has a huge loop, has cut banks over here. And then as it turns here, there's another cut bank here. So what will happen over time is this side's eroding and this side's eroding, and as they erode, they'll eventually meet. And so when the river flows in this direction, it'll eventually just jump this bank. And when it does, the river narrows. So you see how the river kind of flows in this direction, and then now it no longer goes through this entire loop and just jumps it and narrows. So meandering rivers kind of meander back and forth, and then they narrow a little bit, and then they grow and meander back and forth, and then narrow, and that's how they evolve over time. And the kind of leftover forgotten loop becomes a lake, an oxbow lake, which eventually just becomes a swamp and then dries out. But then at a certain point, the river will evolve again and then move and cut through this area over. So it's pretty crazy. Like these meandering rivers kind of meander back and forth. They widen and then narrow and widen and narrow over thousands of years, and that's how they kind of evolve and alter the floodplain landscape over time. Another type of alluvial channel is a braided stream, and a braided stream is pictured here. It's perfect, right? So here, typically, they're at the toe of a glacier or where glaciers used to be. Glaciers are like bulldozers that kind of just push sediment and then leave behind a huge mound. And so when a river kind of cuts through that landscape, it'll cut through in a number of different ways and have this braided type shape. So you can see that here as it almost looks like braided hair, as many different pathways of the water kind of cut through a lot of deposited and unconsolidated sediment. So this will typically form in low-lying areas in landscapes that had glaciers in them. And this is another type of alluvial stream along with meandering channels.